Why doesn't the universe do what it should? Or rather, why does the actual expansion rate of the universe differ so radically from the standard predicted value? For years, specialists have been struggling with what is known as the Hubble tension. But presto! The James Webb Space Telescope detected a very particular cosmic explosion that appears 3 times in the same picture due to the gravitational lensing effect. This discovery allows us to determine the value of the Hubble constant with unprecedented accuracy. However, this revolutionary method of measurement raises even more questions than it answers, and we may have to admit that we are still far from understanding the true nature of the universe. After all, the error is human, and Albert Einstein was only human too. In fact, the creator of the theory of relativity was so convinced of the idea of a static and unchanging universe at first that he even added a cosmological constant to his equations. But when Edwin Hubble discovered the expansion of the universe based on the redshift of galaxies, and when Alexander Friedmann and Georges Lemaitre also found solutions to the Einstein field equations describing cosmological expansion, Einstein was forced to abandon the idea of his cosmological constant. Later, the world-renowned physicist even called it the greatest blunder of his career. Today, the fact that the universe has been expanding ever since its creation is a cornerstone of astronomy. However, the universe does not expand into an existing space. No, rather, space itself is continuously expanding. In principle, the expansion of the universe can be deduced from the objects that are moving away from each other in space. After all, the distance between them continues to grow. However, when it comes to the question of what is known as the Hubble constant, which indicates the rate at which the universe is currently expanding, scientists rely on 2 completely different methods. The first is based on the standard cosmological model and combines our theoretical considerations with measurements of the cosmic microwave background (CMB). This is another relic of radiation from the early universe, created about 380,000 years after the Big Bang, and it still fills the entire universe today. Using this method, the Hubble constant is measured at around 67 kilometers per second per megaparsec, (mpc). A megaparsec corresponds to about 3.26 million light-years, and 1 light-year represents approximately 9.46 trillion kilometers. This means that the speed at which objects in space are receding from each other increases by 67 kilometers per second for every 3.26 million light-years of distance. This represents a staggering 244,000 kilometers per hour per megaparsec. However, this rate could be significantly higher. As mentioned earlier, this is just one of 2 methods for determining the Hubble constant. The other method relies on the observation of objects such as Type 1a supernovae, which always reach the same luminosity, or Cepheid variables, stars whose luminosity fluctuates regularly. In this context, the Hubble constant is not 67, but suddenly 73 kilometers per second per megaparsec. As a result, real observations of space show that the universe is currently expanding at a speed of 20,000 kilometers per hour per megaparsec, much faster than it should according to the standard cosmological model. But how is this conceivable? How does the universe troll the cosmology? This is exactly the question that arises, and the simplest answer might be that earlier measurements were simply wrong. To verify whether we can truly trust the data collected, the Hubble Space Telescope has led a new series of observations using the much more powerful James Webb Telescope. If anyone knows how to understand the accelerated expansion of the universe, it's Adam Riess, who received the Nobel Prize in Physics in 2011 for his work on this very issue. After Webb examined over 320 Cepheid variables, many of which had already been measured by previous teams, the confusion among specialists was even greater. The new measurements of the luminosity and distance of Cepheids actually corresponded to those of previous observations. As a result, the new data also allowed for a Hubble constant that was significantly higher than the one obtained from theoretical models. However, it is clear that there is a problem when a constant is not constant. Not to mention the fact that this constant is supposed to describe the entire universe. At this point, it would be tempting to claim that the universe has trolled cosmology. And Adam Riess openly admits that our understanding of the universe may still be incomplete. We may have simply overlooked something fundamental in our cosmological models. Perhaps there are new types of particles or fields that are as unknown to us as the exotic forms of dark energy and dark matter. This new cosmic explosion tells us even more about the Hubble tension, that old mystery. In fact, researchers have now developed another method to solve this mysterious Hubble tension. This new approach began with a rather straightforward but profound question. What are these three bright spots that had never been seen before in detail? The specialists had identified three luminous structures in the Webb images of the galaxy cluster G165.7 plus 67.0, which had not been detected in images taken in 2015. Eventually, this would turn out to be something very special. It was a single cosmic explosion that appeared as three supernovae due to the gravitational lensing effect. In astronomy, the gravitational lensing effect describes the bending of light by massive objects. In this context, light from a distant source, here a cosmic explosion, is influenced by the gravity of another object that lies in front of it. For the observer, the basic principle here is that the light rays are bent more strongly the closer they get to the mass. In simple terms, the gravity of a massive object acts like a giant magnifying glass in space, distorting the light from structures located behind it. But how did the international research team come to the conclusion that a single cosmic explosion was responsible for the three images in Webb's pictures? Brenda Fry, from the University of Arizona, explains that the corresponding galaxy cluster, called G165, is known for its high stellar mass, more than 300 solar masses per year, and this fact is correlated with higher rates of cosmic explosions. Indeed, subsequent investigations confirmed the initial suspicion and showed that Webb had indeed captured the death of a violent flash of a white dwarf. This leads to a Type 1a supernova explosion. In this type, a white dwarf steals matter from a companion star until it reaches the critical mass and explodes. Since these luminous displays all have roughly the same initial luminosity and fade at the same rate over time, they are considered standard candles, popular among specialists. We have already mentioned the importance of these standard candles in determining the Hubble constant. However, this time, the effect of anti-gravity has allowed researchers to obtain entirely new information. The lens in question is a galaxy cluster with a central arrangement that reflected the image of the standard candle, creating two additional pictures. In fact, the light traveled along three different paths, and since each path was of different length but the light travels at the same speed, the stellar explosion was captured at three different times. To better illustrate this, think of this feature as a triple vanity mirror in which we see three different pictures of the same person. Similarly, in the time-lapse recordings from the Webb Telescope, there is a right mirror in which someone is combing their hair, a left mirror in which their hair is being combed, and a middle mirror where the person is holding the comb. Why trust the increased pressure on the Hubble constant at research institutions? We then realize that such a triple cosmic explosion, with its delays, distances, and anti-gravitational properties, also provides enormous potential knowledge about the Hubble constant. After the experiment, it offered scientists far more information than they normally get. As specialists continue to understand the mysterious rate of expansion of the universe, this cosmic explosion, dubbed TRUST, with a redshift of z equals 1.78, is one of the farthest Type 1a supernovae discovered to date. In fact, the stellar explosion occurred about 10.3 billion years ago, but if you want, it was recently the subject of an astronomical prearranged meeting. This means that a subgroup of the Pearl Research Program undertook to analyze TRUST based on these Hubble constant strain measurements without exchanging their results. The idea was that the corresponding values would be determined independently of each other, without bias, and only revealed at a specific time and date. When the moment arrived for the teams to present their models of anti-gravity, the Hubble constant was found to be neither 67 nor 73, but 60.4 kilometers per second per megaparsec. But what does this mean? On the one hand, the result is consistent with other measurements in the local universe, but on the other hand, it is increasingly inconsistent with values determined for the younger universe. It is worth noting that this was only the second measurement of the Hubble constant using this method, and also the first to use a standard candle. Nevertheless, the value obtained this time differs significantly from the theoretically derived value, and we simply do not have a clear explanation for this. Astronomers now hope to improve the accuracy of their measurements with additional insights from the James Webb Telescope. If Webb's sharp eye can spot other standard candles in the future, the day may come when the mystery of the Hubble strain will finally belong to the past. And if you haven't already clicked on subscribe, it might finally be time to do so. Don't forget to like and subscribe to never miss one of our new videos. See you soon.